In this video, we are again going to be looking at some examples with vectors, and in order to be successful in this, we ought to remind ourselves of this rule for vectors. If we know a vector's magnitude and its direction, then we can multiply the magnitude times a matrix that contains sine and cosine evaluated at the direction, and the end result will give us the rectangular form of the vector, where the component results in the upper component does list the horizontal component of the original vector, and the lower part contains the vertical component of our vector. So essentially what this does for us is when given a diagonal, it computes the horizontal and vertical components of each of those diagonals. And when we have the horizontal and vertical components of each of those diagonals, then we can start combining different vectors together. And so in this video, we're going to use the same techniques as we did from the examples where we were pulling from the physics textbook. However, we're going to be able to answer some questions or find some missing results that we weren't able to do or that we did not do in the last video. So let's talk about this one for a second here. A weight of 800 pounds is suspended from two cables as shown in this figure. We would like to know what are the tensions in the two cables. Well, the tension of each cable is simply the magnitude of each vector. And so hopefully you recognize that this cable here is pointing in this direction as it's pulling, trying to support the weight. This one's pulling in this direction. And then there's a third vector pointing downward because that's the weight of the box. It's pulling straight down, so that's the third vector. So I'm just going to call this vector A, B, and C. So vector A, B, and C. Now the first thing that I'm going to do is establish the angle measures for each of these vectors off of a XY axis, and this is kind of nice because we can just draw it right here at the center. By the way, this collection without the picture behind it, let's see if I can make that disappear for just a second. This is kind of like what a free body diagram represents. We were talking about those in physics class, but if all of the forces are exerting from a single point, we call that a free body diagram. So the angle A, well, 50 degrees is marked in this position, but that would be the same as this position because the beam and this plane are presumed to be parallel to one another, and these are alternate interior angles that are cut by a transversal. So we're going to say that vector A is pulling at a 50 degree angle. So we're going to say A is at a 50 degree angle. B, on the other hand, well, this is 35. That means that this angle down here is 35, but on a 180 degree scale, a 360 degree scale, we would subtract 35 from 180, and that's going to look like 145 degrees. And then finally, vector C, since it's pointing straight downward, we're going to report that as 270 degrees. And here again, all of these angles on a 360 degree scale help us tremendously when we use the calculator to evaluate our results. So let's think about what this would look like if we were to put all three of these vectors together. We would need to know the magnitude of A and multiply it by the cosine of 50 degrees and the sine of 50 degrees. We would need to know the magnitude of vector B and multiply it by cosine of 145 and sine of 145. And we would need to know the magnitude of C, which in this case we do know, and that's 800 times cosine 270 and sine 270. Now, since this object is suspended and not moving, they're calling it equilibrium, or it's called equilibrium if this object or if its center of the free body diagram is not moving. So the sum of all of these forces would have to be equal to 0, or the vector 0, 0. Because when we're done, we don't want any horizontal movement and we don't want any vertical movement if this object is truly calibrated in equilibrium. So the next thing that we're going to go over is how we can determine this result, and we can actually use a matrix, a larger matrix, to solve this. Now, one thing that I'd like to point out is that this result here, the 800 times this matrix, that is going to be easy to calculate, and it will represent a single vector. And so what I'm going to do is I'm going to move that to the other side by subtracting. And then I'm also going to recognize that this magnitude of A is being distributed into this matrix, and B is being distributed into this matrix. And so when I'm done, I'm going to also have a rectangular or a component form of our vector for A and a component for B, and that will end up being equal to some component, which is the opposite of component C. And I say that it's the opposite because this will be on the other side. So algebraically, it may look something like this. The 800 will multiply by cosine 270, and the 800 will multiply by sine 270, and the results of those two computations will be the component form of this vector. The magnitude of A will multiply by cosine 50, and the magnitude of A will multiply by sine 50, and so on. And if you recall from our college algebra class last semester, this may start looking familiar to you, because cosine of 50 is just some number times a variable, and cosine 145 is a number times a variable, and same thing with sine down below. So in a sense, this is going to look something like, oh, I don't know, this is not the answer, but this is synonymous to what it's going to look like, 2x plus 3y, and we may have 5x minus 7y, and in both cases, the upper result, because the upper component is going to have to equal some number, let's say 15, and the lower result might equal another number, say 25, and this system of equations over here can be solved either using row operations that we've practiced in the past, or we can use the matrix. And the matrix, if you recall, can be accessed using menu 7, 5, menu 7, 1, 1. We can actually develop a system to solve, we've got a method that we can use to solve a system of equations by accessing these steps in our calculator. And so that's exactly what we're going to do over here. And to illustrate this point, I'm just going to compute the cosine and sine results over here and rewrite the letter A to be used in place of magnitude A, just for the conversation's sake. So cosine of 50 was 0.6428, and that result has to multiply by the magnitude of A. And again, just for simplicity's sake, I'm reporting that as letter A instead of a magnitude. But I want you to see here, if I repeated that computation for the remaining cosine and sine operations on the left side as well as on the right, now cosine 270 is 0. 0 times 800 is 0. Sine of 270 is negative 1. So 800 times sine 270 is negative 800, although I forgot to subtract this over. So I got ahead of myself doing two steps here. This should have been a negative 800 times each of those components. And so we have 0 and positive 800 as the result here. Now if I can put this expression or this system into a reduced row echelon form command within a matrix, then we can obtain the result that we're after. And so on the calculator it's going to look something like this. I'll call the reduced row echelon form command. I'll create a matrix that says 0.6428 and 0.7660 with negative 0.8192, 7360, and 800. And what we would like to see as a result that produces the reduced row echelon form with ones down the diagonal on the left-hand side, and the solution, the numerical components on the right-hand side, will represent the magnitude of A and the magnitude of B. So let's see what we get. Let's Let's pull up that calculator on this screen now. We'll jump into the menu, choose number 7, and then 5, so menu 7, 5, and then immediately menu 7, 1, 1. We're going to create a matrix that has 2 rows and 3 columns. And we can enter the decimal values. And it looks like I've got all the values entered as I had written them on the other page, so with any luck, the result that we get is reported in reduced row echelon form, which it does appear to be so. And we've got a result here. It appears that vector A has a magnitude of 657, or 658 when rounded, and vector B has a magnitude of 516. And so by setting up this system of equations, we've now determined that, again, the tension in A, so let's see here, where's a good spot to report this? All right, so cable A's tension was 658 pounds, while cable B had a tension of 516 pounds. And so it's kind of interesting, even though the box itself weighs 800 pounds, the weight supported by each of those chains must be greater than half of that each, right? So you would think with 2 cables supporting one box, each one should hold just 400 pounds. But as it turns out, at an angle like this, it does require much more force to support the object. And we can use the same procedure for this example here. The tightrope walker in this particular case is moved out pretty far onto this tightrope. And I don't think this person is in the center here because you can see the deflection of that rope is different on either side. We do have a very similar free body diagram. If the center of the system is right here, we've got 3 vectors with 150 pounds pointing straight down, some unknown tension pointing up at 3.7 degrees to the right, and some unknown tension 4.2 degrees to the left. Now I'm going to immediately change that to 175.8 degrees on our 360 degree scale. And so that we don't confuse this with the work that's on the other part of the page, I'm going to call this vector X, this one Y, and this vector Z. So as far as our setup goes, the magnitude of X multiplied by cosine of 3.7 degrees and sine of 3.7 degrees must be added with the vector magnitude of Y times cosine of 175.8 and sine of 175.8. And that those 2 vectors must also be added with the magnitude of Z, which we know to be 150 pounds. And the direction there is 270 degrees. And since this tightrope walker is in equilibrium, again, the word problem itself doesn't say that, but this little description here is mentioning that. Since the tightrope walker is in equilibrium and not falling, then we'll go ahead and say that the resultant vector of the sum of those 3 is the 0 vector. So this setup is virtually identical to what we saw before. So I'll go ahead and kind of write something here that might get you thinking. We don't actually have to evaluate cosine of 3.7 and cosine of 175.8 along the way. We can actually allow the calculator to do all of that work for us. We know that this result gets pushed over to the right-hand side, and these are going to be entries in a 2x3 matrix. So let's go ahead and call our reduced row echelon form command against the matrix. Now, this matrix is going to need cosine of 3.7 degrees, cosine of 175.8 degrees, And then over here, we want negative 150 times cosine of 270 degrees. And I'm calling this negative 150 because we know that this term does get subtracted and moved over to the right-hand side. We can do that math mentally if we want, but I just want to prove a point here that all of this can be done simultaneously with the calculator. And so the setup here is going to be sine of 3.7, sine of 175.8, and then negative 150 sine 270. So this setup with the calculator essentially replaces this setup that we did in the last problem where we had all of these decimal values, but we only obtained these decimal values after having used the calculator one time prior to evaluate each of these computations. So again, rather than using the calculator twice, if we recognize the pattern and the setup, then we should be able to use the calculator one time and also determine our result. Now, if our result does present in the form of a reduced row echelon form matrix, then we know that the solution in the upper row is going to be our vector x. So we think x is going to be represented right here in the top, and vector y is going to be represented in the bottom on the right-hand side of our reduced row echelon form command. And that's because of the orientation of our system of equations on the left-hand side. So let's see what we get. And so I took a couple moments to enter all of that into the calculator. Cosine of the x vector's angle and sine of the x vector's angle. Cosine and sine evaluated at the y vector angle, and then negative 150 evaluated at the z vector angle. And again, we're using negative because we've now essentially moved that vector to the right-hand side of the equation. When we press enter, we do get a reduced row echelon form of the matrix, so I suspect that these solutions are correct for the magnitude of x and the magnitude of y. It's worth noting that these two results are very close to one another, 1,088 and 1,089, which was a bit surprising at first, but then I realized, well, this tightrope walker is pretty close to the center. The deflection was a difference of 1/2 of a degree, so that seems to me that the angle is, or that the tightrope walker is somewhere in the middle, and so the tension on the right and the left is going to be about the same. Now, if the tightrope walker was here, really close to one side, but still rather far from the other, we'd imagine that the two angles were a fair bit different, and the tensions in each side of the rope might be different as well. But that's not the case here. The tensions are very close to one another. And so as I copy the solutions from the calculator, we've got 1088.4183 and 1089.0744. We again will note that this result is for the tension in the x vector, and that this one is the tension along the y vector. Now, certainly there are other methods that you can use to solve these equations, and if you're researching the process to these types of problems on your own and you're comfortable with other methods, then by all means use them. Just keep in mind that whenever we do work in this class or when we complete our tests or exams, I'm looking very closely at your methods, not just your solutions. So be sure to illustrate how you obtain your results if they differ from mine, or even if you use the same ones. I'd like to see all of your work. I'm going to go ahead and stop the video here, and we'll pick up with other examples in another video. Thanks for watching.